So what I'm going to try first up is a bit of an inclusive introduction. So as Chris said, my name's Caroline Tiddy. I'm an associate professor in geosciences at the Future Industries Institute at the University of South Australia. And I'm presenting to you from home. So you'll be able to see I have a uni SA background and I have on a maroon hoodie and maroon glasses, and I have short, dark, curly hair. I'm speaking to you today from the land of the Kaurna people in Adelaide in South Australia. And I'd like to pay my respects to their elders past, present and future. And I find it interesting as well to think about their Aboriginal peoples and the way that they used, or the way that they have and continue to actually look after their land and the way that they explore it. And I think there's actually a lot that we can learn from what they do and apply that to what we do today, so that we can look after this land that we have now and into the future. So the purpose of my talk is around an introduction to MinEx CRC, as Chris said. And when he contacted me, he said, you know, can you just tell us about the CRC and what you're up to and give us an update on your activities recently. So within the CRC, I am the coordinator of the education and training program, and I'm also involved in research projects within two of our programs that I'll explain a little bit later on. And the research that I do is around development of sensors that will allow for rapid collection of geochemical data, and also looking at what we can actually do with that data so that we can basically be smart about how we use the data and what we do with it, and how can we actually interpret it, voluminous amounts of data. So I'll go into that a little bit further as well. The first thing I'd like to do is change my slide. Oh, I did this before too. Hang on, there we go. The first thing I'd like to do is acknowledge our participants and our affiliates, of MinEx CRC. We have quite a few of these participants and affiliates, and they're really important because they are some of the major contributors to the CRC. So the first thing I thought I would tell you is what MinEx CRC actually is, why we exist, where we came from, and sort of who we are. But in order to do that, I was having a look at the EarthByte group website, and I noticed that a lot of your funding actually comes from ARC. And I thought, wow, if it's, there's all these acronyms, ARC, CRC. CRC is a cooperative research centre. And I thought maybe you might not actually know what a CRC is and what that CRC program is all about. So what I've done is I've actually got a few videos through this presentation. So I invite a few friends basically to help me give this talk. What I'm going to do is show you a video from Tony Peacock. He was the CEO of the Cooperative Research Association until quite recently. If you already know what a CRC is, then please bear with me. But for those who don't know what a CRC is, I'm hoping that this will help. So if you can't hear, by the way, shout out and let me know.
Australia has relatively low collaboration between our business and our university and research sector. It's a problem in every country to build those links, but particularly in Australia where many businesses are not that old. Our university sector was in expansion mode from the Second World War on. First 3 PhDs were only awarded in 1948, so we didn't have a strong history of research, and certainly not of research and business working together. And so in 1990, in the general election, Bob Hawke, the Prime Minister, promised a cooperative research centres program. The program is delivered for the federal government through its Department of Industry, Innovation and Science. And that provides the glue that brings together usually business, public researchers like those from our universities or from CSIRO, to work together on a common problem. For every dollar that the government puts into the CRC program, at least $2.50 come from the industry participants and the research participants. When industry is putting in cash to CRCs, they're also putting in what's called in-kind which is access to a mining site or access to a drilling site, access to farms. So by building that network of businesses, universities and other researchers, everyone gets the benefit of access into the best businesses, access to the best brains. You would form a cooperative research centre where you need long-term research to either open up a new opportunity or to solve a long-term problem. Long-term might be 3 years for computing, but it might be 10 for a medical development. CRCs can range from 7 million through to 75 million. Cooperative research centres operate across science and in many sectors: mining and resources, agriculture, medicine, ICT, the environment, and really any area where business wants deep collaboration with our public researchers to make something happen. Industry wants that source of deep knowledge that is also practical. A lot of the focus is on actually delivering that research. So that could be commercial, it could be through environmental policy, it could be through social policy. They can take the research and apply it in the field at a very practical level. We often find CRCs are delivering critical mass to an industry to really take it up a notch. When a company participates in research with, say, one university, it's a one-to-one collaboration, obviously. But when they buy into a cooperative research centre, they might be working with as many as 15 or 20 universities, sometimes 3 or 4 from overseas, plus a national research agency. You tap into a global network of research and expertise. One of the common threads that every cooperative research centre has had since the inception of the program has been an industrially based PhD program. Not all people that want to study and do a PhD want to end up being an academic. They want to work in industry, and through the CRCs we're supplying a line of talent into industry, and the industry very often employs the PhD students that come out of CRCs. And we often hear from cooperative research centres and their participants that the centre really changed the environment, changed the culture in an industry to one that is more cooperative, where researchers and industry participants are working together for future development. So they often leave a legacy of cooperation, if you like. And very often you find that they deliver things that no one dreamed of at the start of the CRC. And that's why collaboration really works.
So that tells you what a CRC is actually about. And Tony can certainly, tell it in a much more comprehensive way than what I can. So now that you know what a CRC is, I wanted to tell you a bit about why MinEx CRC actually came into fruition. And in order to do that, we actually need to think back to 2008. So, what's that, 15, 16 years ago now. And what people started to realize is that we have this problem where it's getting really a lot harder to actually discover mineral deposits. And a really key part of finding a mineral deposit is actually to be able to collect sample from the subsurface. And one of the problems with collecting sample from the subsurface is the only way you can do it is to drill, and drilling is really expensive. So there were some people that actually came up with this concept of, well, what if we can actually make drilling much more cheaper, faster, more environmentally friendly for mineral exploration? And out of that conversation came the concept of the Deep Exploration Technology CRC, which is the CRC that was the predecessor, so to speak, to MinEx CRC. What I want to show you now is a video that actually outlines where we got to at the end of DET CRC, the Deep Exploration Technology CRC. It was an 8-year CRC, which is it's 2 years shorter than what MinEx is. And what we did was we built the first ever coiled tubing drill rig for mineral exploration. And what you're going to see in this video is a bunch of numbers that's actually going to compare the coiled tubing drilling technology that we developed in DET CRC with traditional types of drilling, such as diamond drilling. So I'll show you this video, and then I'll speak a bit more about those numbers and what we're actually doing now in MinEx. So that hopefully gives you an idea of where we got to. Oh, I've done it again. Of where we got to at the end of 2018, or sorry, mid 2018, when DTCRC finished. Some of the numbers, hopefully you saw them and had a bit of a, and hopefully were surprised about them. The cost of the coil tube drilling was $50 a metre, and you compare that to $250 a metre for traditional diamond drilling. It can be up to $250 a metre. The rig itself is really small. It's only 15 tonnes, and you compare that to a diamond rig, which can be around about 50 tonnes. So you can imagine the footprint of the actual rig is significantly smaller. It's fast. There was rates that are quoted there of 15 metres an hour versus 3 metres an hour for a diamond drill hole that was in exactly that was in pretty much the same spot. So what we did is we actually twinned diamond holes with our coiled tube drill rig so that we could make comparisons like that, because we were drilling through the same geology. The depth fidelity of the diamond rig was fantastic, or of the CT rig is fantastic. We were able to resolve a 1 metre interval of high copper concentration at 400 metres depth. We achieved our goal of being able to drill to 500 metres depth with a vertical hole. And what all of this does in combination is actually open up this concept of prospective drilling, where essentially, because you can have more drill holes for the same amount of money, then you can actually, you can do things such as drill in a grid, so that you can actually start to collect your sample in a pattern, so that then you can actually look at your geochemistry, for instance, and you can actually use that to vector towards ore deposits. So by the end of DET CRC, we knew that, that we'll run to something good. But as with all technology development, it takes quite a long time. And by the end of DET CRC, we had drilled, we had done 2 test drilling campaigns. That was at Horsham and another one up at Port Augusta. So we knew that we had a lot more that we needed to do with this rig in order to develop it into something that's commercializable. And we knew that there's so much more we could potentially do. So out of that came MinEx CRC, the Mineral Exploration Cooperative Research Centre. And so MinEx CRC is the world's largest research effort into mineral exploration. We're a $220 million CRC that is going over 10 years. We have most of our effort is concentrated in either South Australia or Western Australia. The CRC itself is divided into 3 programs, and I'm going to tell you a little bit about each one of those. So the 3 programs are centered around drilling, around sensor development, and then around our National Drilling Initiative, which is an opportunity to test the technologies that we're developing in programs 1 and 2. So I'll tell you a little bit about program 1 first, because that continues on from this development of the coiled tube rig. And you can see that this is a picture of a MinEx field trial, which I'm going to tell you a little bit more about and in a minute. And you can actually see the coiled tube drill rig is that yellow thing in the middle. And then we also have what's called our hydraulic processing system, which I'll show you another photo of later on. What we're doing in MinEx CRC is we're in terms of program 1, is we're looking at how we can make this CT rig better and how we can prove up that technology for commercialization. So we're moving from it being a 500 meter capacity rig to 1,000 meter capacity. This is one of those things that's much, much easier said than done. So there's a lot of engineers that are basically involved in this. We're looking at being able to do directional drilling. So actually being able to drill multiple holes from one point. And you can imagine if you can do that, then it actually significantly decreases the environmental footprint that you would actually make during drilling. We're looking at being able to, instead of just doing the coiled tube drilling, which produces a material that's much like flour, but with chunks of rock in it that might only be about 200 mils big. Along with the coiled tube drilling producing that material, we also want to be able to produce diamond core. So we've been looking at how we can actually have diamond tails on our CT holes, or we can actually do side cores. So you'd actually maybe be halfway down your drill hole, and you can actually get a bit of drill core off to the side. So that's a sidewall core. We're developing I'll just go to the next picture. Here's another picture of it. We're developing, along with the CT rig, one of the big technology advancements in MinEx CRC has been development of our hydraulic processing system, and that's that truck in the background. What that truck does is something pretty impressive, actually. So in a traditional diamond drill rig or RC rig, you'll actually have to dig a sump. And so what happens with that sump is all of the water goes into that sump. So there's water that's used in drilling, and it gets used once in the drilling and it goes into the sump. And it's, you can imagine you're using thousands of litres of water to drill a drill hole. And also the sumps are big, and you're having quite a significant impact on the environment. What this HPS system does, it actually allows us to recycle our water. So the water goes down the drill hole and it drives our downhole hammer, and it comes back up with the sample. It goes into the HPS system. the water, the sample gets taken out of the water and sample mix and rock mix. And then that water gets cleaned and then it gets pumped back down the drill hole. So it's a closed system. So that HPS system is really, really important for water cleaning as well as for the sampling. So this slide actually shows the overall benefits of our coiled tubing. So there's a couple that I've mentioned in there before. There's the small physical footprint, there's the no sumps, there's the low water use, the recycling of water, there's the low carbon footprint. We've actually been looking at how we can, or we've been monitoring how much diesel fuel is used in the CT rig and comparing that to how much is used in a diamond rig. Something that I haven't mentioned yet is that the safety of the CT rig is significantly, well, the CT rig is significantly safer compared to your diamond rig because we've removed the need to actually do rod changes that you would have in other types of drilling. There's nothing moving up the top apart from that wheel that the steel pipe is wound around. That slowly unwinds as the hole is drilled, and then as you pull the drill bit back up, it unwinds. But there's no spinning pipe at the top, so it's significantly safer. We have really good hole integrity, and the productivity is significantly increased because it's a faster type of drilling, and also there's no need to actually do all of those of the putting the rods on or taking the rods off as you go in or out of a drill hole. All of that, of course, is related to cost, and so all of those things together significantly decrease the cost of our CT drilling, which is a huge advantage. When it comes to developing technologies such as this, one of the especially disruptive technologies like the CT rig, one of the challenges is to actually prove up your technology to the point where a commercializing company will actually see that technology as being viable and something that they want to take and then put onto the market. So we're really at this point in MinEx now where we're really trying to test our drilling technology along with some of the other technologies we're developing, as I'll explain to you what those technologies are soon. So what I want to show you now is a video that is actually about some of the trials that we've been undertaking. So this trial was, they're both in South Australia, and it'll give you a bit more of an idea about what we're doing in MinEx for our trials.
August, using a total of 4 vehicles. The site was set up and ready to drill within 3 hours of arrival, occupying a space of 18 by 18 meters, which were fenced for security and walled by hay bales on one side to reduce the noise disturbance to a neighboring property. We commenced drilling on the day of arrival and were drilling on site for 10 days, operating in shortened day shift to ensure minimal disturbance to the Kapunda community. After 2 weeks of drilling, we spent additional 5 days field trialing some of the new RoXplorer sampling and locking technologies that has been in development since 2019. Deepest existing hole at Kapunda is 120 meter deep, and during the time we spent at Kapunda, we were able to color and drill a 290 meter vertical hole through partially weathered to fresh basement rock, including 80 meters drilled in 9 hours. Mitigate, regain circulation and continue drilling after 3 lost circulation events, during which circulation were lost to highly broken fault zones. We were able to capture drill cuttings over at 1 meter intervals over 90% of the drill depth with rock and textures and mineralogy, including visible sulfides suitable for visual locking. Color and drill a 50 meter vertical hole designed to enable a field trial of our coiled tubing drilling selective coring device and capture material in the core barrel for the first time. We're also able to deploy and test our locking while drilling smart bottom hole assembly with the integrated positioning tool utilizing Vasara technology and prototype locking while drilling gamma tool designed by the MinEx Project 4 team. We're also able to deploy conventional gamma and gyro tools as a part of the coiled tubing drilling locking workflow. Lastly, we managed to train and educate the second drill crew on the new drilling, locking and sampling systems. The Kapunda drilling exercise has provided invaluable experience and allowed us to improve the technology and refine drilling processes, data capture and sampling workflows on site. Since Kapunda, the CT rig and HPS have been mobilized and deployed in the Delamerian National Drilling Initiative campaign near Kurunda, 100 kilometers east of Adelaide, applying the learnings from Mawson Lakes and Kapunda, but in a very different drilling condition. For the first time, operating the RoXplorer system in 24/7 operation, including remote internet operation of some of the systems. The MinEx RoXplorer drilling team first drilled, sampled, locked and cemented a 335-meter drill hole, including casing through 235 meters of complex cover rocks, and operated a record 12-hour shift with 165 meters drilled. Secondly, the team drilled, sampled, locked and cemented a 310-meter hole in only 3 days. The field trials are driving rapid growth in our understanding of the CT drilling platform, testing new technologies and how to maximize productivity and sample quality whilst maintaining a safe and sustainable drill site. The drilling trial at Kapunda would not have been possible without the local engagement and support from EnviroCopper, Bridget at the station for housing us in her newly renovated railway station.
So I might leave that one there because at least it's a thank you to all the local people in the Kapunda area. But hopefully what you caught from that is that some quite impressive numbers, where 3 hours from when the crew actually arrived to the drill site, 3 hours later they were actually drilling. That's significantly a significantly less amount of time compared to other drilling technologies where it would take 1 or 2 days to actually set up. There was 14 meters an hour drill rates through some tough conditions. And to us geoscientists, this was a really important field trials because it was the first time that our coring tool was actually tested. Soren also, who was the speaker in that video, Soren also mentioned some sensors, and I'm going to come back to that a little later on. So let's actually talk about some of the geology or sort of advantages around what MinEx is doing and what we're up to in that geoscience sense. So this is a photo from the one of the sites at the Delamerian NDI. The Delamerian is sort of east to northeast of Adelaide, just through the hills and sort of out into the Murray Basin, just to the east. So the type of material that that geoscientists need to work with the coiled tubing drilling is these cuttings that are shown on the left there. So I mentioned before, it's a bit like a rock flour, but then you've got some kind of 2 millimeter chips in there. You can get a lot out of these cuttings. In that set of trays that you can see there, you can actually see that distinct color change. And that is related to different types of regolith or different types of geology that has actually been drilled in that hole. And that material, even though it is a rock flour, we can still get a lot of information from that. We can get geochemical information. We can get mineralogical information. There are some key pieces of information that or data that we can't get from the CT cuttings. We can't get things like structural information. You know, what's the orientation of our faults? You know, are there any folds in that? You can't see that kind of information. But what we have done, as I mentioned before, is we've actually developed a tool that will allow us to collect drill core at the bottom, currently just from the end of our hole. So it's like a tail is what we call it. And examples of that drill core, just to prove, you know, evidence to show that I'm not lying, is actually shown in those other two trays there. So you can see this drill core, it looks like any other drill core you would get from diamond drilling, but we're actually doing it with our CT rig. And it's been up to about 3 meters or so that we've actually collected. And of course, from that material, we can tell a lot. This is some close-up examples of what the information we're getting out of out of that drill core. So we're able to see lithologies and actually, really understand those lithologies in detail in terms of their mineralogy, their grain size, metamorphic textures, igneous textures, all of this kind of information. We can see things such as alteration signatures. You can see evidence of things such as some epidote alteration through here, for instance, and we've got a lot of hematite alteration as well happening within these samples. So we can actually start to get that kind of information out. And of course, this material, you then might decide, here's a really interesting rock. I'm going to actually go and use that for my geochronology, or I'm going to be able to take thin sections of it and do metamorphic petrology. So having that core ability to collect the drill core is a huge advantage that has been developed within MinEx. Because I'm aware that this group kind of really likes big data sets. So I thought I'd throw this in here. And this is with all of our national drilling initiative projects that are happening within MinEx CRC, we are ensuring that all of that data becomes publicly available. So the Delamerian National Drilling Initiative is actually the second NDI case study that we've done. The first one was actually up in Tyza, so between Tennant Creek and Mount Isa, and that was with Geoscientists Australia. And then this one being with the Geological Survey of South Australia, they've actually developed a web platform whereby you can get all of this information on the MinEx NDI drilling just at the click of a button. So there's things there such as maps, and then all of that data in terms of the logging of the lithologies, in terms of the geochemistry. This is from Portable XRF. It's all available within this drilling atlas. And other data is also available through an online portal, data portal that we have with MinEx CRC, and that's actually available through our website as well. So there's all of this information that is becoming available, and it's all about data. And continuing on that data theme, I want to sort of pause on the geology side of things just for a sec. And I want to bring you back to the second of our programs. So I told you about the first program, which was drilling, and then I've sort of told you a little bit about the third program, which is our National Drilling Initiative. And the second program we have is actually around development of sensor technologies that will allow us to collect some really cool types of data whilst we're drilling. So the types of technologies we're developing are things such as using optic cables that will actually go into the drill string and can be used to collect data around seismics in the drill hole, and actually uses the drill hammer itself as the seismic source. We're also developing technologies that will allow us to collect petrophysical data whilst we're drilling. We've also got projects that are looking at how we can do automated 3D modeling using some of that data that we're collecting from those sensors, and doing it really quickly. So if you've got a lot of data going into these models at once, being able to automate that 3D modeling will mean that you haven't got to wait for the geologist or somebody else to actually sit and do that modeling, and it takes a lot of time. And the one that I left to last, which is the one that that I'm sort of involved in a little bit, and I can tell you a little bit more about, is a project where we're looking at developing a sensor that will allow us to collect geochemical data down a drill hole. This project involves researchers at UniSA and at CSIRO. And what I've got here is a presentation that, or a video that we actually put together earlier this month or last month, that actually explains where we're at with this data, with this sensor, and it actually shows you what it is. So I'm going to play that, because I think it's a bit more effective than me kind of trying to just tell you about it.
The first real-time downhole assay prototype based on LIBS technology has reached the first stage of real-world testing, which is analysis of a simulated drill hole in the lab based on real lithologies from the field. The very ambitious aim of developing a novel, real-time downhole elemental analyzer has reached an important milestone: actual testing in a simulated laboratory drill hole. The four main parts of the project that have been progressing in parallel, which are the LIBS hardware, LIBS calibration from real lithologies, dual spectrometer software, and data analysis and modelling, are now sufficiently advanced that they will be incorporated for the first time into a real-time downhole analysis platform.
The LIBS hardware, laser, optics, and spectrometers has been incorporated into a very narrow probe that has undergone a variety of tests and is now ready to be lowered into an accurately characterized set of drilled ore blocks and will allow elemental analysis of a vertically oriented drill hole. The experimental setup allows for a range of contaminants to be introduced, as would be expected in a real drill hole.
The 21 accurately characterized ore blocks have been evaluated by various independent analytical techniques and can be assembled vertically into a synthetic drill hole and used to compare the results obtained by the downhole prototype. Part of this work also involved developing LIBS calibration for major and minor elements in our second LIBS lab at UniSA, further strengthening our understanding of LIBS analysis of typical lithologies. The data analysis and modeling aspect of this project has a range of novel components, incorporating artificial intelligence and machine learning. LIBS spectra will be degraded to various degrees by typical drill hole contaminants, and modeling the changes will give us an ability to accurately reconstruct the underlying composition. Finally, bespoke software that allows dual acquisition, control, and analysis of the dual spectrometer hardware are now at the beta testing stage, allowing spectral data to be instantly stored and handled remotely. The ability to obtain real-time elemental composition of a deep drill hole will dramatically reduce the time taken for the analysis to be incorporated into a commercial exploration campaign. For the first time, it will allow the results of one exploratory drill hole to directly influence the decision for the placement of subsequent drill holes.
To that one. Now, hopefully I can. So that tells you a little bit about our downhole sensor for geochemistry. And it uses LIBS, which is laser-induced breakdown spectroscopy. And what I want to show you here is some work that was undertaken by one of my PhD students, and he's published it in the open access journal Minerals. And what he's actually done is he's shown how you can actually take the raw LIBS data, which is what's shown on the left here, and you can basically turn that into a downhole stratigraphic log. So what he did to show you the comparison, this is a visual log of the, it was basically a series of rock blocks or little rock slabs that were glued together to form a pseudo stratigraphy. And this is the visual log of that rock slab. And what Fernando managed to do is, from taking that raw LIBS data, he used a program out of CSIRO called Data Mosaic. Some of you may have heard of that before. And he managed to actually show how you could use that LIBS data to produce a pseudo stratigraphy that is actually quite similar to that visual log of the actual rock slab. This was the first time that anyone had tried to do this. And what it showed was that there's real potential for this LIBS data, this spot analysis data, to be actually used in logging of the rocks that we're actually drilling. The other thing that you might have noticed from that video was that there was that really long tube. What we've had to do is actually redesign the way that a LIBS instrument works so that we can put it into a configuration that would allow us to actually put it down a drill hole. And it's been pretty exciting to actually be a part of that, I've got to say. So you can imagine the opportunities that having rapid downhole geochemistry would actually open up in the mineral exploration campaigns and for mineral explorers and geologists in general. This is something else that we can do with the data. I'm quite conscious of the time, so I'm actually not going to show this video, but what it's about is showing something else that we can do with our geochemical data is we can use it to actually create augmented reality type software that will allow us to visualize our geochemistry or our hyperspectral data on core trays whilst we're logging them. So this video is actually available on the MinEx CRC website as a quarterly update. So you can actually still see that, but the technology is, it's pretty cool. It's very new. It's not been developed very far, and it's been done by some researchers at UniSA. But yeah, check it out if you're interested in that kind of thing. Oh, there we go. The other type of thing that we can actually do with our geochemical data is this is something that that I'm more involved in with the research within the geoscience research in MinEx. Is we're actually looking at how we can use the geochemistry so that we can be smarter in terms of vectoring towards ore bodies. And so one way we can do that is to develop an understanding around how we can use the chemistry of specific minerals to target ore systems. So what you can see here at the top left is a table that actually shows our general knowledge level of different types of minerals and how we can use their chemistry to target different types of ore systems. And you'll see that there's some that have actually been we've got really well-defined global criteria for. And that's mainly for the porphyry systems. And a lot of that work comes out of UTAS and the people down at Codes that have been spending a lot of time looking at those porphyry systems. But being in South Australia, we're actually quite interested in iron oxide copper gold systems. After all, we've got Olympic Dam, Prominent Hill, Carrapateena. So there's keen interest in IOCGs here in South Australia. And some of the work that we've been doing is looking at how we can use the minerals monazite and zircon, which are really quite common minerals, to understand how we can vector towards IOCG deposits. So what we've been doing is looking at establishing the background chemistry of both monazite and zircon and other minerals as well. And then looking at the chemistry of those same minerals within ore deposits and basically just comparing the two and trying to understand what the difference in chemistry is, if there's any at all. And so this kind of work is, we've actually got a paper in minerals, two papers in minerals, sorry, both published last year, one by myself on monazite and another by my PhD student, Adrienne, where she was looking at zircon. And within MinEx, we actually have quite a collective effort of actually looking at these different minerals and at different types of minerals and different systems, depending on who we're working with, and understanding how we can use them. My husband just started talking, sorry. The other thing that I think is really important that MinEx CRC is doing is looking after its most important asset, which is its people. It's one thing that I'm really quite surprised with within the Cooperative Research Australia is that, so Cooperative Research Australia has 26 CRC members. Only 2 of those have visual equity, diversity and inclusion sections on their website where they're actually visibly and publicly showing that they are proactive in the space of EDI. And I'm quite proud to say that MinEx is one of those 2 CRCs. The other one is SmartSat CRC. So what we've actually done within MinEx is we've undertaken quite a few activities that will continue through the life of the CRC. We've done things such as develop an EDI action plan. We've developed an EDI policy that is actually now available on our website, and as is a code of conduct. And the kind of activities that we're working around is doing things such as being mindful around meeting participation and the types of presenters that we have at each of our meetings. We're doing things such as on some of the videos you might have noticed, hopefully there was some subtitles. So in our later videos, we're actually starting to do things like that to make the products that we're actually, or the communication that we're delivering, a lot more accessible to everybody.